welcome. On this channel, I do unscripted, unedited videos about Linux programming and stuff. I am both in the process of relearning C and focusing on a particular little game project here. Today, in this video, I am going to kind of dive down into some of the technical decisions that I need to make around this project that I am just starting. I explained, at least partially explained, this project in the previous video, in video 23. It is one of the primary, it is a multiplayer network game, and one of the primary components, one of the primary restrictions that I'm putting on the creation of this game is that all of it will run on a single server, on a single host. And one of the most significant issues that I have with that, of course, to deal with, is zero downtime deployments, or as the case may be, choosing not to have them. I mean, it just depends on which way we go here. So I want to dive into that and then start to define some of the experiments that I'm going to do to guide me in making that decision. The first thing I want to do, though, is to create the Git repo for this thing. So let's do that really quick. So where's the button? New repository. We're going to call this Space Captain. It will be a public repository. And there we go. I have not initialized it. Oops. So it's git init. Let's actually add something. Switch the branch to main. That step is kind of wasteful. Default branch already is main. I didn't need to do that. Okay, so that's what I wanted to double check. In the future, it'll always be main. So git remote, I just need this part. Git remote, add GitHub. I always like naming my repo remotes where they go. And then it's just git push u origin. There we go. Okay. So at this point, we have a repo with nothing but a README in it. This repo kind of defines the game. It's kind of a blending of an EVE Online, Dwarf Fortress with a sprinkle of Factorio. That's probably the way I'll continue to explain it for a while. But the thing I want to discuss or to work around is in the deployment process, we have some options here. Ideally, why does it think this is a cargo app? Well, I guess there's no, yeah, there's no files here for it to decide from. Or why does it think it's a Rust app? Okay, but I am going to turn off Copilot. Okay. Okay. So I want to do a little bit of exploration to figure out how I'm going to do the deployment process and kind of build up what my goals are here initially. it has to run on a single host. I could use a reverse proxy. So one option is have HA proxy sitting in front of the service, and I can literally do then blue-green deploys, right? So that's actually complicated because to me what that does is it means, might not be obvious, but now all of a sudden the state of the game has to be in a third process. Because if the blue and green are switching, the state is not inside of those processes. The state is somewhere else. And so you would likely end up with some memory DB type thing, which could be Valkey, or it could be anything really. It doesn't even have to be that structured, which is holding the state. Now, what that means also to me is that any access to the state is now going through the network layer, and we're probably introducing nearly an order of magnitude, 2 orders of magnitude in delay in every time that we access anything about the state of any of the entities in the game. Okay, so right off, that's not a preferred path for me, although it seems, certainly it would work and it would be performant enough, and even, running on a single host, we're doing pretty good here because we're only ever doing local host network access, right? But what if, option 2, what if we build all of that into the process? Or no, let's not even go that complex. Okay, so one option is there is downtime. So small downtime, I'll call it. You literally, you literally restart the process. So let's say that the game is listening on, let's say we're listening on port 8080. No, that'll make people think it's HTTP. It's not going to be HTTP. So let's just say we're listening on 4343, right? Some random number. And why would I do that when I could do 4242? So we're listening on 4242. We have one process listening on 4242. We restart. Next process, it shuts down. Next process comes up. It's listening on 4242. What we have to do to make that work well is small downtime, resilient clients. So the clients, if they're relatively stateless, nearly completely stateless, they lose their connection, they reconnect. Maybe they, make some requests to rebuild a small amount of state that they're holding, and they just keep on chugging. Now the goal here is you're going to want to minimize, and this is actually where I'm likely going to be heading. We want to minimize the time between processes listening. But I haven't solved. Now this potentially can be an approach for the networking side. One client shuts down, lets go of that port, and the other client starts up as fast as possible. But we haven't addressed the memory side. Where is the data? If the data is entirely in the client's memory, well, if the data is in something like Valkey, it's in a memory database, then no problem at all. The second process comes up. It also connects to the memory database. It has a live look at the database. And so we could even do a hybrid there. So a minimized time between listening processes, and maybe with 2 here, we use memory database. Okay, but we can also go further. We can do minimize minimize downtime, and we can handle the database, the data. I don't know how to refer to it. The data transfer. It's easier for me to explain the idea than it is to give it a name right now. So the idea would be, I'm going to walk out the whole idea. Okay. We have process. We have the. I'm going to do this as a blue-green. Blue process is running. Part of it running is that its operation. All operations happen through wall. So all operations happen through a write-ahead log. So what's going to happen is the client is going to connect. So again, we'll call it out. I don't know that the clients are truly stateless, but they're very small state. And I'm going to refer to them as stateless for the time being. And what that means is the clients are mostly sending commands. They're saying, I've clicked on this. I've, they're sending the input stream almost directly unedited, unprocessed from the user. User clicks on something, we find out they click on it. User moves something, we find out they move it. User types command, we find out they type the command. The client doesn't hold a huge amount of state. It doesn't process the state, and then it just transfers the request to change the state, and then it can ask questions in response. And in fact, I'm going to call that out. Part of this design is we split up sending. We're going to split writes and reads is what I'm going to call it to the database essentially. So if a client says, "Hey, I clicked on this," it doesn't really get any information back about that. It just gets an okay. I got your request, or a network error, right? That's all it's going to get. And the reason for that will become a little bit more obvious as I go on, but we're synchronizing everybody's input into frames so that most users, regardless of network latency, are going to feel the exact same thing. The game isn't Twitch, it's near real time. By design, there's going to be like a half-second delay between the request for actions and those actions happening. And so when you request an action, it can't tell you the outcome of that action until that next frame. And so what it does do is it just says, "Yep, I got the message." And then next, the client can, when it feels it needs to, it can say, "Hey, I need an update on this piece of information," or maybe we're just pushing it down. Probably we're just pushing it down. In fact, almost certainly we're just pushing. We know what we expect the client to have currently, and we just pass it a diff for the state that it needs to know about. So every frame we're saying, here's a diff, here's a diff, here's a diff, here's a diff. And the client is simply, when it has input, it sends a message, and then it responds, shows to the user the output based on that diff. Is this a high idea? Maybe. I've never written a game before. I don't know anything about it. I'm more, and realistically, I'm just more thinking about it in terms of, a network process. Okay, so we split the reads and writes. It probably can ask questions, but it's going to get streamed. So for the most part, the server is streaming state diffs, and I guess either the server or the client at any time could say, "Whoa, here's the full state." because it might think we're one or the other might think they're out of sync. And we'll probably have a mechanism where, we're serializing a count or something like that for messages received so that they can feel if they dropped a packet or anything like that. Which brings us to, if we're going to chase extreme speeds here, we probably should just be doing UDP and handling the network loss ourselves. So we would know when it's truly necessary for things to be in order, etc. Okay. So I'm going to jump back though now. That was a little bit about how the networking works, which we needed to know to discuss how restarting the process of sharing memory works here. So so I have the blue process that's running. These are just kind of some notes, but what's going on, in fact, I'm just going to, that's not super relevant right here. All operations happen through a wall. So what's happening is user sends input, activate this unit or activate this feature. And that gets written to the wall. And then the client is going to respond with, got it. But then what's happening is in half-second chunks, in frames, behind the scenes, the game is running. And it's going to read everything off of the wall that's been recorded for that chunk, and it's going to process it all and update the state. And then it's going to send all of the clients, it's going to stream out that state diff to all the clients. It'll be interesting to see what that pulse looks like in the network traffic and how big of a problem that is. I'm not going to try and address it now, but we may get to a stage far in the way far in the future where we do the calculation and then we look and say, oh, we have 400 milliseconds before we have to do this again, and you stagger the outputs to some degree so that you're not doing a huge pulse right after. So I'm speculating about the far future. That's not necessary right now. And that speculation didn't even sound so good now that I'm thinking it through. Blue process is running. All operations happen through a wall. Now, what we're trying to work out is the startup and transfer to a new process. So we start the green process. So we have a running blue process. We start the green process. We point it at the wall. So it reads the wall. Actually, I'll explain how it gets there. First, it's going to read the previous state dump. Then it it reads the wall until it's caught up. So, right, there's going to exist a state dump. Here's just a finite file. This is one file that represents a point-in-time dump. There is a point-in-time state dump that happened in the past. There is a wall that proceeds from that point in time forward that identifies every action that every client will take. And so you start the green process, it reads the point in time, it starts to process the wall, it eventually catches up. Then what it's going to do is it's going to signal the blue process and say, the signal meaning, hey, I'm ready to take over. The blue process at this point is going to, here's the interesting thing. It doesn't even need to finish anything that's in process. All it has to do is have written, every connection has to be in one of two states. You've written it to the wall and returned, okay, we're going to do it, or you don't write it to the wall and close the connection. That's all there is to it. So blue process, return okay for everything written to wall, close connection for everything else. Right? That's all it's going to do. Blammo, and go away. Now, and then the very last thing, though, I'm going to say is write end of file to the wall. And I actually don't just mean close the file. I actually mean you're going to write a marker into the wall. And what's going to happen, actually, at this point, all network connections are closed. We've already let go of the port 4242, right? And so the other process is going to be reading the wall. And so at this point, what it does is it sees the end of file marker. It's going to open port 4242 and now it's the primary process. I don't think they're right. So it's going to write end of file. It's literally going to shut down. I'll write it different. I have a horrible time with this keyboard. I'm going to end up replacing it. I switched keyboards not too long ago, and I don't know. This one just does not fit my fingers right. It's just off in some small measure. Terminate process. And I just haven't. I've been using it now for about 2 months, and it just doesn't fit right. Okay, so this is the thing that I want to explore. In other words, this reverse. I only put these here really to explain the problem with trying to go this route. This one, in both of these, really, the primary problem ends up being that you're using a memory database. To do it, you probably have to use a memory database, and now you have the network latency to talk about any of the state of the game. And I want the state of the game in the game. Actually, I don't even need that. Let's do this. That didn't work out for me, but, him to the rescue. So this ends up... Okay, this keyboard is killing me. This ends up being the thing that we want to do. So now, how do I prove this out most economically? Well, I need to write a piece of code that's going to open up a port and listen on it. I think that the thing that I want to do is to actually have it have some minimal functionality. So we're going to create kind of an echo process that takes connections on 4242 and just echoes back the request, right? It's pretty straightforward. And we can improve on this in the future, but I can have a couple of these running and I'll be able to see, the hiccup that they go through. One of the things that I'm trying to determine is how long is that downtime between processes, right? Now, I'm talking about a game that's going to have a half-second frame, a half-second frame rate, basically. And if that little hiccup right there can be brought down to several milliseconds, then it just is not a factor inside of what's going on. If it only takes a couple, let's say 200 milliseconds for a client to say, oh, I got to reconnect, right, and do that. There's not much ill effect. Having some ill effect is okay. We're living on a single server. Our alternative to this is to actually probably have downtime. Well, our alternative might be to go back to a memory database, but before I would do that, I would end up doing some really critical analysis of the timing performance between memory reads and the in-memory database. If it's 2 orders of magnitude, it's just out of the question, and I think that it is. Okay, I also have to recognize that I'm putting a bunch of big burden on myself here. We actually have to, almost entirely glossed over it. In fact, I did gloss over it. The state dump. So, so this is where the state dump comes into existence. When a process shuts down, it flushes out the wall, and its internal state then should completely exactly reflect what it would be had you read up to that point in the wall. And so then it writes the state dump. Notice that this particular state dump is not the one that the green process was using. The green process actually started with the previous state dump and then read that wall. Because this state dump doesn't, we're trying to minimize the time between the writing of the end of the file in the wall and the running of the new process. So yeah, we could say, hey, write the whole thing and start up from reading it. But now we have the delay of I have to read it, get all my ducks in a row, then start accepting connections. That's guaranteed to be more time than, oh, I seen the end of file marker. Okay, I've already got the state read and accurate. Now I switch over. Again, I should probably do measurements around this to see just how big these are. This is the idea, and this is kind of where I'm going to start. And if I find I have issues, then I can start to explore out from there. Okay, details. What does it look like? Echo server, right? So the server opens, listen on 4242, echo anything sent. It has to maintain a state, which could just be an account of connections. And it has to have a function for, well, it has to create and stream the wall. Maybe what we'll do is we'll have the clients, maybe it's like maybe the state is more than just a count of connections, but it's a running sum of it's a running sum. Oops. Where maybe the clients send a number, an integer. Server responds with sum. the wall is just a stream of integers to add, and some enums, which well, actually, and some the wall is a stream of integers and the end of file. So it's going to be, the wall is going to be like, let's say it's a byte stream, and its wall is a tagged, it's a tag struct that is either an integer or end of file for now, right? And so that's what we're writing out. And then the state dump is just the current sum of numbers or whatever other information we're keeping track. Okay, so on start, some of the things that we need to do, just kind of in no general order here, is we need to be able to load a state file. We need to be able to read a wall and update our state accordingly. Need to be able to send a signal to other process. We need to be able to, close reading wall, open writing wall, on signal. We need to be able to open and listen on socket. The server needs to respond to signal to terminate. So the client is a little more straightforward. It connects to, for now, it just connects to localhost on 4242. It connects to host. Might as well let it take a full host. It connects to a host on 4242. Generates a random 1 to 10 digit and 1 to 10 integer, and sends to server. It's going to get read state update, read and update state. So the server is going to be sending a stream of state updates back. It has to be able to read and update its state, display it. When disconnected, needs to reconnect. In both cases, respond to in the case of the client, I think SIGTERM, you know, really we probably are. You know, so you both need to send it and respond to SIGTERM. I think that's how that works. So this is the basic pieces then that I'll be creating in the very, very near term. We're going to create the Space Captain server. We're going to create the Space Captain client. These are the basic goals for what each of those processes can do. The goal is going to be write it like it is the foundation of our future project, but the actual really core goal is to determine if this idea about terminating and picking up off of the wall can respond fast enough to be our future deployment process. Or if I should go back and consider actually using a memory database. That is the plan. So again, not really very much code going on in this one, but we will start with code in the next one, right? So this is, I will start with really dumb TCP server client applications, and we'll go from there and build up this functionality. We'll define this list a little bit better as we get going. I need to decide on exactly how I am going to represent the project, right? I am used to living in a world of Jira at work. That is not how I want to do it. I mean, but I do need a similar process. I need to make sure that when I identify work that needs to happen, I don't lose track of it, that it gets back into into a prioritized backlog. In fact, I probably will just create a backlog.txt and do a sentence or paragraph per item and just have it stack ranked, and that will be the backlog for the time being. Anyway, that is all for this video. We'll pick up on the next one with actually writing some code for the Echo server. I will see you then.